Hi everyone, welcome back. So we're back to this tunnel again. So we have a blow-down wind tunnel. We got it all the way up to 20 atmospheres, and the temperature of the reservoir is still at 300 Kelvin. So that's what we did last time in our last problem. And now we're going to have it expand to a point where the pressure drops down to 1 atmosphere. So what we want to figure out is two things. One, what is the temperature at this location if it was isentropic, or if it wasn't isentropic and we had entropy increase of about 320 joules per kilogram Kelvin. So first one we use our isentropic relations, the second one we just use our basic entropy relations. It's not going to be hard, it's kind of a plug and chug problem, but it's very interesting what we find out. Okay, so first off, let's use our isentropic relations. We have a ratio of pressures, 20 and 1. We want a ratio of temperatures because we have the first temperature, we need to find the second. And we already know what the specific ratio of specific heats is. That's just going to be equal to 1.4. So we plug that in and rearrange a little bit. What we can find out is that my temperature would come out to be 127.5 Kelvin. Okay, that's just a number. You can see it dropped, pressure dropped, temperature dropped. Seems fine. Now, what do you think is going to happen when we have it be non-isentropic, when we are starting to increase entropy? Do you think this temperature is going to go up or is it going to go down? Well, let's find out. So we're going to use our TDS relations. We have a ratio of pressures, and so we use the one that has a ratio of pressures in it. And we can use that to calculate our temperature here. As a note, if you want to do a bunch of algebra for these kind of problems, you're welcome to. Otherwise, just plug in some numbers and start canceling things. Like this is just a number, that's just a number. I could divide this over here. It's a lot easier if you just plug in the numbers, simplify as much as you can, and then do your algebra. You don't need to do all the algebra right at the beginning. Sometimes I will. I'd like to show you that sometimes, but you don't have to. So we plug it in here. I put all the numbers I have. This comes from the table. You should really memorize this number. And when I do that, I find that my temperature is, what do you think? Higher? Is it lower? The answer is it's higher. Now, why do you think it's higher? Well, I kind of already tell you there. The reason it's higher is because more energy went to those internal modes that I can't really access, rather than increasing the airspeed. So when I have inefficiencies, I'm going to have hotter air, but slower air, okay? Hotter air, but slower air. You can see this if you actually look at your total energy equation. So I'm going to use E here. I know that we use E for internal energy here, but I run out of symbols at some point. So for my total energy, there's various terms. It's going to be equal to the enthalpy plus the kinetic energy plus the potential energy. That's usually the terms I can have other ones, but I'll go with that one. So we have no change in potential energy here because, as I mentioned, any changes in height. However, we know it's a supersonic wind tunnel. It has to be getting fast. It goes from a reservoir, the velocity was 0 to begin with, to some sort of velocity that is, who would have guessed, more than 0. So that kinetic energy term has to increase. So what we're seeing through this is that, if I have, E where S is equal to 0, my enthalpy term is going down and my kinetic energy term is going up. Because, the total amount of energy is the same, it doesn't change. If I have my entropy where, my total energy equation where the entropy is more than 0, the delta S is more than 0, then what I'm seeing is since my temperature is higher, my enthalpy has gone up compared to my other case, and my kinetic energy must therefore go down. So I have a slower flow. So we want to remove those inefficiencies to speed up our flow. Another way of thinking of this, I'm just giving you a lot of ways to think about it, is where is all of this entropy being generated? There's a lot of places, but one place that's probably pretty obvious is friction. And what does friction do? It slows you down. And what does it also do? It heats things up. When you rub your hands together, you feel them getting warmer. Why do they get warmer? Because of friction. Okay, so that's it for this example. I just want to keep on coming back here because we're going to build this up a little bit more next time. I just want to show you how entropy is affecting our flow and why these calculations are really important. Hopefully this helps you. I'll see y'all later. Bye-bye.